Thank you, Zain, and colleague in the project of enhancing resource ecosystem services for inviting me for this event. And then, the title of my talk is Mangrove for Resilience. That the aim is to show you or to sharing you on the modeling approach on mangrove eco-hydrogeomorphic interactions. So then, I heard from Zain that most of the audiences are, let's say, already familiar with mangroves. So then I think that I don't need to introduce you more on mangroves because you already know a lot and maybe already having this mangrove, let's say, living side by side by you for all the time. So then, basically, the mangrove is district that it is located in the intersection between the sea and land, and then they are like federally influenced and also Southern trees. But something that is I think that's most important is they are really diverse in species. Even though, let's say, Avicennia marina in Indonesia, it can be different with one in Suriname, for instance. And even their like a physiology is also different. And what really interesting to me as an engineer, because basically I'm an engineer by training, that I'm really interested on how can we parameterize the properties of mangroves into our model. So let's say what will be the effect of the certain properties of mangroves to the hydrodynamics, and whether can we value this to some extent, for instance, for coastal protections. And because of that in my work, I'm really focusing more on the mangrove interactions between the mangrove and also with waves or tides or even the nutrient exchange and so on. So for instance, here, like we have this video for USACE, that they demonstrated that where we see the interactions between waves and mangroves. And maybe you have heard before that the role of mangrove as coastal protection, when these mangrove forests, they can help to attenuate the waves, considering the, let's say, the width of the mangrove belts and also the composition of the mangrove itself. So then by looking at this, then we can understand like multiple roles of the mangroves. So maybe in my presentation here is a bit, let's say, narrow focus, that I look more on how the role of mangroves into the function on the wave attenuations, and how can we say, let's say, what will be the role of mangroves into the carbon sequestration function. When we look at this figure, that it is really clear that the composition of mangroves, the dimensions, and also their volume will help us to giving more volume or giving us to more blocks to help to, let's say, dampen the waves by looking at this. And then in addition to that, that the mangrove can also act as the, let's say, carbon sink when they help to cap, let's say, this let's say slow and wave can help to, let's say, have to settle down all the sediments, and these intricate routing systems will help to also to capture the sediment into the bed level, and they somewhat to lock it. When then this locking mechanism somewhat can be called as this carbon sink function, then they can be sequestered, then the carbon can be sequestered as sediment depositions. And in addition to that, the carbon can be also stored into their biomass. Then it will be like a double function on this carbon sequestration. When but these interactions can somewhat be more interesting, especially when in Indonesia, is as a case study that we have this in the northern coast of Java, that previously people are living there, and then these people are really dependent on the mangroves itself. And then when at first they look at mangroves as just a barrier of them, because they need the land, they need to convert it into the aqua stream, let's say that as the shrimp pond as part of their aquaculture practices. So that at the beginning they start to cut down the mangroves and then also try to open the space and then let the water in. But eventually, time by time, you know that there is interaction between mangroves, let's say, waves and muds. And even though this, let's say, wave action is a bit low energetic, but still it can, let's say, transport the sediment. See, and then by, let's say, cutting down all the mangrove forests, you see that this like a really fast erosion of of the land, that even in within 10 years you can see that there is a lot of loss of land up to the hinterland just because of losing the mangroves. So then we see this is the crucial roles of mangrove as coastal protection, because once we see the cut-down of the mangrove, then we see this really fast, like say, moving dynamics of this sediment transport moving away from the land to the sea, and there is no way to return it back. So, to understand more, then we need to see that how the mangrove and soil are interacting, and not also that we see that mangrove is also a living being, meaning that we need to understand the life cycle of the mangrove itself. So the interaction of the mangroves can be presented in these vertical layers of soil, I believe. So then I'm abducting the chart from the Kraus et al. Work, that in this chart we can see that we can divide the processes between mangrove and soil into the three important layers. The first layer we can call this as a subsurface layer. This subsurface layer is somewhat hidden to our eyes, but they hold the long-term processes. So in this scale, we see that there are like a different, let's say, uh, dimension of the processes. The first one is subsurface processes that are taking longer term. It can be annual to decadal time scale in form of soil compaction and expansions. So the soil can be compacted because of the heavy load of the sediment above, and also the mangrove itself. So then it is compacted and getting, let's say, deeper, or it can be also expanding depending on how the load is actually working on them. And then the more active surface, that the most active layers that we can see, this the surface processes and also the seawater. Then this is the two layers that we are always see. Then in the surface process, we can see that there is, let's say, the exchange of the energy from the water, that this water is coming from the multiple sources as well. So we can see the effect of waves, the effect of the rivers, and then the effect of tides, that they somewhat like mixing it all together. And if the energy is high enough, then we can see the erosions. And the energy is low enough, then we can see the sedimentations. And we see that this is the most, I mean, the most interesting layers that maybe in our field is that the most look for, because we want to understand how the effect of these interactions. But in this layer, there are also, let's say, really dynamic as well, because we see the, let's say, the matter of seconds because of the waves. The wave has like a really, let's say, 9 to 12 seconds of periods. Then we see that we see the interaction in seconds, or even it can be like in weekly or even monthly scale, when we are looking at the tidal scale, that we can like driving the water in and letting the water out in the cycles. So then the process is really dynamics from the hydrodynamic itself. And the second thing is also we see how the mangrove is also interacting with the light availability and precipitation. So from here in only, we can see the interaction between the biotic, which is the mangrove itself, and also the abiotic from the, let's say, hydromorphodynamic processes. And to add more complexity, the mangrove itself, they are also a living being. So we need to track the life cycles of the mangrove. So let's say if we can imagine that the mangrove is like a human being, then the adult tree is the adult. So we are like the adult of the mangrove. And then we get married and then and start to produce the offsprings. And then the probable is like the baby, that they are really, let's say, we need to take care of the baby. You cannot be really cold or really warm, and then we have to really hold this really tight, because otherwise if it is, let's say, get fall, then suddenly you can see that the effect of the physical, the physics is really, let's say severe. Then when the kid is, or when the baby itself is growing bigger, let's say as a toddler, then we can imagine as like seedling. So then the results of this baby to get hurt is also getting higher, right? So let's say they can fall, they can walk, and then somewhat like they can climb and, let's say, fall from the trees, but this is still fine within the limits. And then they can grow into, let's say, into teenager, which is sapling. So looking at this, we can see that in every stage of the life of the mangrove, they have their own results to survive. So let's say as a propagule, then they are really sensitive to water circulation. So let's say if the let's say if it is during the high tide, so they just floating around and there is no way to strand. And when it's in the lower tide, and then when the environment is good, they are, let's say, they are dry a bit long enough, which is what we understand as the window of opportunity. So let's say in 4 or 5 days dry, then they can start to develop their routing system, and they can encroach into the new lands. And then even though when they are seedling, let's say, when the wave is not strong enough, then there are no erosion, they are not toppled. Or even though, let's say, if the sediment is high enough, then the seedling can be buried. And even this burial or even uprooting or toppling relationship is also, let's say, having their own results. So let's say if the seedling is still young enough, then they're only sensitive on toppling or even in burial. Then we can imagine that they are still toddler, let's say 2 years old, 3 years old. Then they have different own thresholds. But when they are only reaching the teenager, they are strong enough. Their rooting system is deep enough, and then their stem is big enough. Then they can withstand with the more stronger forces of the environment. They can withstand on the, let's say, the stronger wind, the stronger waves. Then they can survive there. Then the survival of the mangroves is also sensitive to the life cycles. So we cannot only look mangrove as a static system, but they are more dynamic. Then that's why in the model we are trying to incorporate this dynamic of the mangrove, how the mangrove will, let's say, respond when they are still in propagal stage, what happened if mangrove is still in seedling stage, and what happened when they're in sapling stage, and what will be their, let's say, their expansion functions. And by understanding that, then we can start to judge. Maybe I will not say judging, but let's say start to quantify whether mangrove is actually, let's say, ecosystem engineer, meaning that they are building their own environments, which is that we can do nothing, then we will survive, or they are actually opportunities. So basically, if the land is still there and the environment is good, I will just grow. So the meaning that we have to create a proper environment for mangrove to grow. Otherwise, then they just die, because basically they are opportunistic. So then, but in order to understand that, then we need to know. So then the main objective of my work is I want to gain a better insights into the complex eco-geomorphic interactions and the feedback processes in mangrove, in order to develop a trustworthy tool to predict the dynamics. So then, again, back to the first slide, that I'm an engineer. So people always ask me, okay, Sebrian, so what happened if I plant this mangrove, this species, Avicennia, right now, for instance, and I plant this mangrove in this plot? What happened after 5 years? What happened after 10 years? And then there is always the question that they ask to me. Okay, in order to answer that a bit first, we need to understand the interaction first and the feedback processes. Then we understand that. So what parameters is important, and whether should we build a really complex model, or is a simple one is already enough. It depends on your goal, right? So then, to understand that I developed these 3 steps on answering the question. First, that we need to understand the time scales of the mangrove, because let's say, should we look at the time scale in annual time scale, or should we look in seasonal scale, or even should we look in the smaller scale? Because when we look at this image, we see that the wave, it has the second scale, let's say it has a really short scale, just in seconds, let's say 9 to 12 seconds for waves. And tides, they have a bit longer, so let's say weekly or even monthly scale. But morphodynamics, they are even longer. They can be yearly. And mangrove, they can even more longer, because you see that mangrove itself, they have like let's say a bit. I would not want to say, I don't want to say slow, but it is a bit longer time scale. It can be decadal time scale, right? So then first we need to assess, like, how about this mangrove dynamics timescales, and how to do that. Well, it is not, not possible for us to measure it by hand, because first, it is swampy areas, you have mosquitoes, it is also difficult to walk. And then when you ask laborers to help you, then you need to spend a lot of money to do that. Then it is the beauty of technologies, and we are now blessed with cheap UAV system, We have abundant sources from remote sensing analysis, even in Google Earth Engine, let's say, in the Microsoft planets, and even more sources. Then what happens if we can combine those, let's say, the hand measurements, the more very high resolution UAV, and so in the medium resolution in satellite imagery. And by looking at these time scales and also the interactions by using these remotely sensed data sets, then can we try to develop a model? And I choose this what so-called the spatially explicit model, because why is it spatially explicit? Because it is varying in space, and also this space variation of forcing, then it will be explicitly having the interaction also and also the feedback. And in order to do that, then I incorporating this so-called individual base model coupled with a process-based model in hydromorphodynamic. And then the last thing is, okay, we have the model. So the next question is, can we try to evaluate the current practices on restorations? And what will be the best way to optimize the design of mangrove restorations? With the main target is to optimize the carbon sequestration function. But of course, we could not see the complex one. Let's see with the simplified one. Can we use this as a model or template for another, let's say, restoration strategies? Well, this is a very brief resume on how can we retrieve the mangrove biophysical properties from the sky. So this is a bit old paper, I would say. It's 4 years ago. It's published in 2021. And this paper is basically trying to find a way on how can we retrieve the number of the mangroves and also the canopy height, and can we also couple it with the more medium resolutions on satellite imagery and see the seasonal developments? Because, okay, maybe it is, the product is not really new. You see that we have like this Global Mangrove Watch report, that they have these annual reports on mangrove development, but it is annual. But what I observe is like in Indonesia, that we have the seasonal variation of mangroves. When we see the growth of mangrove during the rainy season, and then the recession of the mangrove extend during the dry season. And we are asking question how and why it can be happens. And the weapon that we use, or the tools that we use, is we use the off-the-shelf UAV drone, and using this structure formation photogrammetry to build this 3D representation of mangroves. And when we are also using this, let's say to detect the mangrove by using this 3D representation, by looking at this minima and maxima point, and then we can see and we can count the tree on the specific areas. And by using this, then we can train our model. In my case, is by using the random forest approach, by coupling the Landsat and Sentinel-1 and 2. So we compile the SAR product and also the optical based product. This is how we integrate this. So then we get this like 11 years of development by combining all the products from Landsat 7, Landsat 8, Sentinel-2. That is basically the let's say the optical satellite systems, and then the Sentinel is the radar system. Why we do this? We choose to do this because in Indonesia, especially in Porong, it is always cloudy. So then we can only see the clear images only during the dry season, but it is almost possible during the wet season. So then that's why we couple it with the Sentinel, in which it is capable to penetrate the clouds. And then we use the UAV, which is the more very high resolution image, to help us to classify the let's say the mangrove images from the satellite imagery. So with that, we can get the mangrove expansions, the mangrove expansion rate seasonally, year by year. I mean, let's say in 3 monthly basis, and by that, then we can develop the age map of the mangroves. So this is the let's say the illustration of how the mangrove is actually growing rapidly. So you see that maybe in 2009 to 2010, they are not really growing so fast, but since then we see that this is very rapid expansion of the mangroves. And then we can see how the mangrove is like breathing during that is growing during the wet season and like when having the recession during the dry season. And this is the, let's say, the more, let's say, detailed description on that. So I put this, I count, or let's say classify this into these two polygons, the larger polygon on A polygon and B polygon. So why did I choose this? Because A is somewhat more mature mangrove forest. They are there for a long time. I mean, in these parts. And then the B is like the newly developed mangrove. So then, as a context, then in the hinterland, why this delta is growing so fast? Because in hinterland, we have this. Maybe you heard this before or not? That back in like back in 2009 or 2008, there is a disaster. So then there is a mining company. They are mining trying to find the source of the gas, and then they mine this location, and like almost at the same time there is an earthquake occur, and then after this event there is a mud explosion on that part. So then we see that a lot of mud explosion in this location, and the mud is there is no chance for mud to be stopped, and then this extra mud flow is basically giving us like extra sediment that is flowing to the downstream. So that's why we have this delta expansion is going to, let's say, growing so rapidly because of this extra sediment coming from the mud explosion. And then what we see here that even this A and B, they have almost similar pattern in which that they have this, let's say, the positive development of the mangrove and also the negative development of mangrove in almost in seasonal, let's say, trend. But the general trend is they are always rising. They are always, let's say, gaining the the new area of the mangroves. So what can I explain for this? That first, that the mangrove recession only occurred at the end of the dry season, while the mangrove is recovering and return to expansion in the middle of the wet season. So as a context, that the dry season is happening during April to September, and then the wet season is from October to March. So what we observe here that by the end of the dry season, the mangrove we see that the mangrove is degrading. They are we see the dieback of the mangroves. And the dieback is recognized as the signal of recession from the satellite. So we see that there are no mangrove in the pixel. So we see the recession. But like in the middle of the wet season, we see that they are growing back. They are recovered. So what is happening over there? So what I see that basically the Porong Delta is creating somewhat like a lagoon system. So during the wet season, we see that extra precipitation from the rain, and we see that the water is a bit fresh. They are fresh. So then the mangrove can survive more in the condition. In addition, that we have like a lot of discharge from the river. So this extra discharge give us like a more chance than for probable to floating more to the seaward side. And then by having this more discharge plus sediment, then you see by the end of the wet, I mean like in the middle of the wet season, we see like the extra sediment in the seaward part. But during the dry season, there is almost no flow at all from the river. So the river is somewhat engineered. So then in the middle of the part of the river, there is barrage that they close all of the gates of the sluice gates during the dry season in order to divert the water into the neighboring city. So that in the northern part of this island, we have this big capital city called Surabaya, and they need a lot of fresh water during the dry season because they have more industries over there. So then in the upstream of this river, the government or the institution is close of the system, close of the river. So all of the fresh water are is diverted into the city. But during the wet seasons, because of the huge discharge from the let's say from the rainfall, then they open the gates in this river, meaning that we have almost full capacity of the river flowing into the downstream along with the sediment, and they close off the sluice gate into the city. So we see that almost zero discharge during the dry season, and almost like a huge amount of water during the wet season. So that's why we have this. We suspect that we have a lot of, let's say, salinity during the dry season, meaning that there's this new, maybe new saplings are died because of that. So we see the dieback of the saplings. But when the let's say when the mangrove is surviving the dry season, then it is highly probable that the survived mangrove tree, they can still grow during the wet season. So that's why we can see this is the positive development in general of the area of the mangrove along the year, even though we have this recession and also recovery trend over the season. So the key take-home message of this work is that we could not see the mangrove development in annual time scale. It is better if we can look at even more detail in seasonal time scale, because by looking at this, we see that there is a lot of variation during the dry and wet season. And just by looking at just 3 monthly development of the mangrove, we can already see the, let's say, the difference during the wet season and dry season. So that I can imagine if you can, let's say, having this monthly observation, then you can having more clear image on what is happening in your uh, case study or study area. And then another benefit that we have is when we can create an age map, meaning that the red one is the older one, and then the blue is the new one. So then this dark blue image, meaning that they are 1 year old forest, let's say, with respect to November 2019. And then let's say this one is even older. So then we can see what is the expansion pattern of the mangrove forest by just looking at this let's say seasonal mangrove map. And then by even looking further by using the UAV, that we can see that we have this difference between the North Delta and South Delta, that we can see the connection between the mangrove height and their age. And what can we see here? So then in the Northern Delta, we see that they are, let's say, having a steeper line on the height versus the age, but not so in the Southern Delta. And what can we see here, that the Southern Delta, they are a younger community in comparison to the Northern Delta. So in the Northern Delta, they are like I believe like a 3 or 4 years older than the Southern Delta. And this pattern looking, I mean, giving us a hint that they are having more mature mangrove communities over there. So then they're having this more stable line. But in this Southern Delta, then the connection between height and also age is still not really, I mean, they are still trying to catching up with the other, and it's more saplings rather than the adult trees. Okay, so then we have this information on the development of mangroves and also the delta by using the satellite imagery, meaning like a remotely sensed data set. And then we are trying to model it. So how can we do that? So then we know that the mangrove is living in the habitat, meaning in the landscape scale, where the water and sediment and then let's say nutrient, they have these long-term interactions. But we also need to attach our mangrove there. So then I coupled the landscape scale process-based hydromorphodynamic model, JF3D, with this individual based measurement model. And then this model can talk with each other with this with the Python script, let's say, powered with the BMI approach, meaning like if you heard of the BMI is something like the standards that looking on model is just like your car. So every time you enter a car in any brand, you always have the same steering wheels. You have the same, let's say, gear control. You have the same sign. You have the same wiper control. Then you don't need to think to read the manual again. When, let's say, I have the BMW, you have the Mercedes, you have the Toyota. Every time you enter, you always can drive immediately. So that's the idea of the BMI. Even though you have different model, different way on developing it, but you can use the BMA protocol to talk with each other because it has the same control system. Okay, that's the in the technical term. And then how can we do that? So let's say in mangrove ecosystems, they have these two drivers on controlling their growth. First is the physical drivers. That is clearly the fluvial tide waves and sediment transports, and the environment drivers in which that we call it salinity condition, the nutrient, lights, and availability. And what will be the response? So the response of the mangrove ecosystems with physical drivers, the response can be the wave attenuation effects, how the flow can be altered, on how the morphodynamic will be changed. This is the response of the mangrove ecosystems to the physical drivers. And what will be the response of mangrove ecosystems to the environment drivers? So what happens if salinity is really high? What happens if nutrient is limited? What happens if the light is also limited? Then the response could be in the physical terms is in the soil nutrient balance and in pore water salinity. But right now, this what I have this hatch block is not yet available in the model. So we somewhat not still working on how can we put it into the model. But the another response in the biotic term is the response on mangroves. And the mangrove itself, they have these two response. First is the mangrove growth, meaning the response vertically that they can grow, how fast they can grow, and in the lateral expansion, so how fast they can expand their area. So then, uh, when we are looking at the mangrove growths, then they also have this somewhat so-called 3-to-3 competition. They are competing with space, they have the competition with nutrient, they have competition with their, let's say, their mangrove colleagues, their mangrove friends. So then this is the way on mangrove can, how can we control the mangrove growths because they have these fights to space. So let's say one mangrove tree is living in very fast pace, they can grow optimally because they are not competition. But once we have another companion that's very close to them, then these two trees will compete to the space, to the nutrients. So let's say the small trees will grow so slower because basically this larger trees is absorbing more nutrient than the one. This is what we have. This is what we call 3-to-3 competitions. Or maybe in another paper, let's say in like a Berger and Hildebrand, they introduce this Zoe zone of influence when you see that there is like a the radius of a tree that they can, let's say, affecting the another neighboring trees. So then we can then introduce the mangrove mortality. So let's say what aspect that can control the mortality of the mangroves. So in this sense, in the paper that I would say that if the mangrove is not growing in 5 years, then I would say you are dead. Then you are no longer growing. You just stuck there. Then you will be a remnant on the model. And then we also take into account the probable dispersal and the pioneer establishments by and then with these two with these two techniques, then we can see how mangrove can recover. And then the recovery of the mangrove is dependent on the parental trees. So the bigger they are, the more propagules are produced. And then by looking at the tidal circulation as well, so let's say how long this propagule can be floating around, and then if the water, let's say if the window of opportunity is good enough, so then the let's say the propagules can be stranded on the area and then it can grow immediately. So that is somewhat like the idea of that, and it's in the more technical terms. Then I couple the depth visible mesh that is controlling the landscape-based model that we can see the interaction between. It's more on a physical term. That is how the wave will be interacting with the sediment and how sediment will be transported and how it will be, let's say, settled and so on. And then the mesophone is dealing only with the mangroves, how the mangrove will grow vertically. See? So that in the beginning that we know the initial setup of the mangrove. So we can see the mangrove position and the properties, the DBH, the heights, species. And then we can translate this as into the Brook-Drake coefficient, like the coefficient that is, let's say, slowing the flow and also altering the flow. And once we determine the bulk drag coefficient, then I put this information into Delphi, and then the Delphi will calculate this, and we can have the new water level, the new salinity, and the new morphological change because of the presence of the mangroves. And then by looking at the water level and morphological change, then we can calculate the window of opportunity. So how let's say how good the mangrove, what is the probability of the mangrove to stay there on and then let's say how let's say what is the odds of the probables to survive in the certain cell. And then we are also looking at the salinity, that is the, let's say, the parameter to control the growth as well. And then by looking at the tidal circulations, this is the tidal circulation current, and we can see how far the probable can be transported or dispersed. And then we put this into the factor of reduction factors for the growth, and also the seedling establishment. So then how successful the seedling will be established. And then we put this information into the mesophone, and mesophone calculate the vertical growth of the mangroves. And then it will be determined whether this the bug can survive or not, or maybe determine whether the sapling will die immediately or it can survive after 5 years. And then after the looping, after the loop, then we can get the final position of the mangroves, the height, age, depth, and species. So we see that we have this two loop over here. This is the inner loop. Basically, this is the loop that is taking into account this smaller time scale of the hydromorphodynamics, which is seconds to week. Let's say that seconds meaning the wave time scale, and it can be weekly in the tidal time scales. And then once we have this information, then I put it into the outer loop, meaning the mesophone. So mangrove individual base model is really heavy. So then you do not want to run the model in every, let's say, 1 minute, because 1 minute time scale for mangrove is too small. You cannot see the growth at all. So then the time scale for mangrove is 3 months. So let's say I get this all the information on after 3 months, and I feed it into the model. So I'm looking, okay, by looking at this previous 3 months, then I can determine whether the mangrove will grow in the certain number. That's it. So then this is how I put it into the model. So I have the model, and then I slice it into tiles with let's say 10 by 10 meters. So then in this tile, then we can get information of the salinity and also the window of opportunity value. One is high probability, zero is not possible for you to stay there at all. And then I plant the mangrove, let's say virtually, and then we can see the interaction between this. So this is the schematized model of the Porong Delta. You see that the Porong Delta is having this funnel shape model, funnel shape delta, that we have this small delta in the beginning. Then I put the vegetation over there by mimicking the first density of the mangroves, and we see how mangrove is growing. Then this color is giving you the information on the tree heights, and then the circle giving you the information on the canopy. So you see that this is in the middle of the mangrove. We see let's say the older mangroves that are growing, and we see that they have almost let's say 2 meter high. And the beauty of the model is we can see the instant expansion of the mangrove. So before you see that is like a bare land, but afterwards you see that there is a new community that is actually let's say occupying the space. And then we can see the interaction as well. Then the presence of the dense mangrove, they are altering the flow and making this let's say channel is even deeper, because they are limiting the space of the flow. So you see that we have this a new mangrove, and they are expanding seawards and landward. You see that there is like varying space, right? It is depending on the tides. So when that is strong enough, they can carry the probable further away from the parental trees. And then it also having this effect to the downstream when the sedimentation is occur. So this is a simple model that only have two discharge conditions, the wet and dry, and then a simple astronomical boundary, just M2 with 1.2 meter when the phase is 90 degrees. And in the beginning, we have this uniform salinity in 25 ppt, and the sediment concentration is varying as well. So this is the result of the model. So I'm somewhat happy with the work. This is the shape of the model. So this is what is the shape of delta that we want to, let's say, to achieve. But of course, this is a very schematized model, so we start with the very elliptical model. But what we see here, that is the shape of the mangrove forest is somewhat similar to the one that we see here. They are like a flowing like to the seawards. But for the height, I'm really happy that the model can, let's say, imitates the real observation that the observer height is almost okay with the simulated height. So in the term of mangrove good vertical mangrove good, the model is working okay, is good enough. But in let's say in the lateral expansion, since this is a schematic model, they are not really let's say having the same shape of as what we have here. But I think the let's say the tendency is almost the same, that we have this pointy, let's say, shape in the landward and more elongated in the seaward. So what is the message of this? So then we have like one, two, three, four, five, six, seven, eight scenarios by varying the salinity condition and also the sediment concentrations. What we see here, like in the first 29 years, I mean, all of the scenarios having the same pattern. So we could not see the difference at all. But after 29 years, we can see that they are developing their own routes. So then the red one is this one. When the salinity is low and the sediment is rich, we see that the area of the mangrove is the highest. But when the salinity is high and sediment is poor, then the mangrove area is the smallest. So we can see the effect of sediment supply and salinity to mangrove area development. So then by looking at this, we can see if we return to the first argument that we have in the settled imagery, that we say, okay, because of the lagoon life, then during the dry season, you see there is a dieback of the mangroves. And by looking at this, we can see that the model can somewhat replicate the finding that we have. And well, this is the resume of the all, that we have the high salinity and sediment in the left side, and high salinity and sediment in the middle figure, and the low salinity and sediment in the right figure. And we see that the more uh, the better environment, then it is the best for mangrove to grow. And in the beginning, we see that the mangrove in the young, let's say the young community, they are more opportunistic, so they could not survive without a proper environment. But while they are growing older, their compositions, their biophysical properties start to having effect on the environment. So then we can see the feedback, and we see that they start to say to change from the opportunistic to ecosystem engineer. Next is we try to find information whether the mangrove can play effect to have an effect to the carbon sequestration. Because what? Because yeah, the mangrove ecosystem, they have 3 to 5 times richer in carbon rather than in terrestrial forest, meaning that they have a lot of function. They have the largest function on capturing the carbon, right? And it is a big issue in Earth, in the whole world, that we are trying to reduce the let's say the green sorry the carbon concentration in our atmosphere. And the carbon, and then the mangrove can act as a carbon sink if the environment is correct. So the let's say the carbon can still be in the, let's say, in the soil if the mangrove is waterlogged, if it is always inundated, then the carbon is not released back into the atmosphere. But what we have here, let's say in the second image, let's say what we observe in the map, for instance, in my first image, that they are cutting down the mangrove forest, meaning that there is no more protection to the coast, and we see a lot of erosions, and then the soil is exposed to the air, and what it was carbon sink is now becoming a carbon source, because the carbon is not longer captured in the soil anymore. And then another thing is globally, that we have this global push in advocating green belt policies, that to 2030, that the mangrove cover should be increased by 20%. But we are now in 2026, and what happened in 4 years? What can you do to improve that? And another thing is like 80 to 90% of restoration are failed. So the report said that the trees are dead, they are dying or stunted seedlings. And why it can be happen? Because most of the time, the restoration attempt, they don't look at the mangrove species. So they just grab the mangrove seedlings that they have and then just plant it there. So then, most of the time, they have the mismatch of the mangrove species and the poor understanding on hydromorphological systems. So let's say we have this highly inundated, let's say, wetland. So then you could not just plant the mangrove there because they will be die. They will die because it is highly inundated. So you have to make sure that this, let's say, inundation frequency is correct for the species to grow. So then we are trying to optimize the mangrove by looking at the strategies. So we apply the model into a very simplistic domain. Just let's say having this a simple rectangular domain when we try to plant the mangrove in different elevation. So then we try to put the mangrove above the mean sea level. What happen if we plant the mangrove just right below the mean high water nip? What happen if plant the mangrove in the high water nip and just below the high water spring? And what happen if we put the patch or gap in between? Because every time I ask the community, so in which location that you want to plant the mangrove? In any locations, as long as the legend, I just plant it. Then there is no, I mean, let's say manual on how and or where should we plant the mangrove. So then I ran the simulation for about, let's say, 20 years. And then what we see here, this is the graph that the x-axis giving us information on the simulation time in year. And then the y-axis is the distance. So then like 4,000, sorry, 0 is in the offshore and 4,000 is in the onshore. So then I average the bed level development along the longshores, and I average the x direction into just one value on the bed level, and then I put it in the time scale. So then what we see here that the system is already like positive. So then every time, I mean, the system is always growing. So then even though without vegetation, you can see the growth of the mudflat itself. So it's keep growing. So then I start the model with let's say the quasi equilibrium mudflats. So at first I run the mudflat in the linear let's say elevation, and I expose it into a uniform wave, and then with flow or with tides, and I run it for about 120 years, and I get this equilibrium, let's say concave shape uh, of the mudflats. And whenever we put the perturbation on this, and we can see whether the system is disturbed or not. Because before it is they are in equilibrium, so in the same forcing that they are always giving us the same shape. So when we put the mangrove pretty close to the mean sea level, what we see here, that we see a lot of loss of bed level in the offshore. And the mangrove itself, they are still doing good by capturing the sediment, but at the back of the mangrove forest. And when we plant the mangrove higher, let's say above the high water mark, then the effect of this is less. So you see that the bed level is still like growing, expanding, but they are not really, let's say, if you compare this with the no vegetation, they are still less. But when we put it more above in the high water nip, then we see that the system is gaining more sediment than before, and we see that the mangrove is growing, and then the sediment is also keep, let's say, expanding over there, and the pattern is also the same. What we see here that the mangrove is almost having the same width over the time, but the effect of the bed level is a lot. So then when you plant the mangrove near to the mean sea level, then we see a lot of loss of carbon because of the erosions. So what you see here is somewhat like illusions because you plant the mangrove is growing really green and white, but actually you lost a lot of carbon because there are a lot of erosion at the front. So why it can be happens because we can so this is the profile of the bed level. You see that in the scenario A in no vegetation, this is the pattern of the bed level, that the bed level is always increasing in every year. So this is how it is increasing. But when you put the mangrove really close to the mean sea level here in the yellow line, then you lost a lot of sediment in front of the mangrove. The mangrove is still having a good job by, let's say, capturing the sediment, but they are limited here. And so if you put the mangrove even higher above, then you can see that the sediment is captured within the mangrove forest. And it is even better when you plant the mangrove in gaps. So for instance, here you put the mangrove in gap, then you see that you have these two, let's say two bulges that it is they capture the sediment inside here, and also in the second part of the mangroves. So how it can be possible? That why that basically if you imagine the mangrove is just like a wall of the breakwater, then during the high tides, then this the mangrove at the back, they are somewhat like dampening the weight, dampening the flow. So then you see that there is like a pressure gradient. And during the high tides, the tide in front of the mangrove, they are already high enough, but it is still low in the back. And they need time to start to flow into the mangrove forest. So by the time when it is during the slack period, then it is start to changing to the low tides. Then the water that is still already still within in the forest, they are still they having like to flow back to the, let's say, to the seasides because the friction effect of the mangroves. So then you see that there is a pressure gradient between the water in the forest and water in the mudflats. Then this pressure gradient giving us more extra velocity that giving this effect that there is a lot of erosion to the in the seasides. Yeah, it can be explained by this graph. You see that is at the let's say in the station one, which is a bit in the seaward side, we see the balance between the, let's say, when the during the high tide and low tide, then the velocity is the same. But when it is so like, when it is start to reach the frink, then we see that it's a bit skewed. Then it is more seaward dominant than the landward, giving meaning that there is more flow to the sea than to the land. Then these tides will flushing away all of the sediment back to the sea. And then when we look at the mangrove populations, then we see that in scenario B, that the mangrove population is peak maybe in after 12 to 15 years. Then afterwards they are declining, meaning that there are no chance for the mangrove to expand anymore. So there is only the mature mangrove trees that they are there. So there is no more chance for the offspring to stay in the plots. But when you put it in higher place, so let's say in just below the high water level, then you have longer period for the mangrove to start, let's say, declining. So for instance, here maybe after 17.5 years they start declining, and D they are still having a chance to grow. But when you put if you plant the mangrove higher enough, let's say in high water need and in water spring or even in gap, you see that there is still a chance for the mangrove to keep expanding. So you give space for mangrove to grow basically. So then in gaps, so let's say in the front row, then you see that it helps to dampening the waves, giving you a chance for the sediment to settle here, you see. And then in the second row of the mangrove, they make an advantage of these extra elevations to increase the window of opportunity for the propagules to settle there and then to let's say to establish the new population in the new land. So then there is a tactic to help to grow the mangrove. And then this is also the distribution of the diameter as well. So you see that in the beginning, so let's say in the year 10, they are not so different. But after in year 15, you can see that in the scenarios, let's say in the scenario B, this is only the remnant of the older trees, but we don't see the smaller population there. But when you have if you plant the mangrove high enough and in the gap, you can see that there is a population of the smaller trees or younger trees that are there. So they have a chance to replace the major mangrove trees in the future. And there is a chance for them to expand. So then, let's say in correlation to that, this is the graph of the biomass. So then this solid line is Avicennia and the dashed line is Isopora. So I simulate two different type of species. And what we see here that in terms of biomass, they are not so different in 20 years. So you see in all scenarios, when we only take into account biomass for carbon, they look the same. But it is totally different if you look at the carbon stock when you also take into account the soil organic carbon. Because of the loss of sediment in scenarios close to mid sea level, then in total carbon stock you have is very small, even to compare with no vegetation. So you see the effect is large. So the graph above zero is the biomass and below zero is soil organic carbon. So in terms of biomass, they are not so different, but in terms of soil organic carbon, you see that there's a huge difference just by looking at the placement of the mangrove. So then the higher the mangrove is planted, then it is the higher chance for us to have more soil organic carbon. And gaps also help us to gain more carbon in between. Then as a summary, that what can we see here that we observe the seasonal variation on the mangrove dynamics, and we can model the mangrove, especially by using spatial ethics model by coupling the landscape-based model, for instance, by using hydromorphodynamic model Z3D and also the individual base model by Misofon. And we can also use this model to optimize the restoration attempts. Yeah, this is all. And you can read in more detail into these following papers. If there is any question, just let me know. So thank you. That's all.